Hello everyone. In this video of vibrations, we are going to talk about several important topics. The first one is called modal analysis. The second one is period of oscillations in system with several degrees of freedom. And the third one and fourth one are properties of mass and stiffness matrices and properties of mode shapes. So stay tuned for a good video of several important things that you need to know in vibrations, especially when the system has multi-degrees of freedom. And here we are going to look at the vibration system with basically only mass and spring, and it's free vibrations. There is no external force here. And the picture here is coming from this website. They just posed it as like a problem. Can somebody answer this? Can somebody show me how to solve this? Here we go. So if you are after vibrations and you want to know more about this, here I'm going to solve this problem, and I'm going to explain a lot more than you probably ask in the website. So let's see what we can learn here. First, what is modal analysis? Modal analysis is a technique to decouple the equations of motion of a complex system like this, which has three separate ODEs, but the ODEs are coupled. If, as we're going to see, each ODE, for instance, if you look at the motion for x1, you also see in it x2 and x3. The same for x2, you see x1 and x3, and for x3, you're going to see x1 and x2. So you have to solve those coupled ODEs together, or you can decouple those ODEs, turn them into three ODEs that in each one of them you only see one variable, one new variable, of course, not the original ones. And so you get three decoupled ODEs. You can solve them individually, and then once you have these individual solutions of these new variables, then you can turn them back into the original system and get the original solutions. And I'll tell you what I mean. But the goal is to decouple a set of coupled ODEs and solve each one of them separately and independent equations, so you can see the vibration of each one of them individually. Okay, so it makes the analysis a little bit more, I would say, efficiently. So to explain all of that, all of these topics, let's go through an example. So here we have this mass spring system. The motions of the masses are x1, x2, x3. The values for the masses and the springs here, I provided some numbers. These are not in that website, so I just made up some numbers. 6 spring, 3 masses. This is a 3-DOF system. And what we want to do is first we want to find the mass matrix in this system and the stiffness matrix in this system. Basically the equations of motion. We want to find the natural frequencies of the system, the mode shapes of the system. We want to find the period of oscillation in the system. And we want to find the response of the system to these specific initial conditions, right? You know that you need 6 initial conditions because we have 3 second order ODEs, and we want to do it with modal analysis. We're also going to look at whether the M and K matrix have specific properties, and what about the mode shapes? Do they have specific properties? And whatever we extract here is not limited only to this specific system. They are applicable to any system which has this type of equation. That's the M matrix times the acceleration vector plus the K matrix or the stiffness matrix times the displacement vector equals 0. So any system of this format, any result that we derive here is applicable to them. Remember, the M is what we call the mass matrix and the K is what we call the stiffness matrix. And the solution here is if X at time 0 is given to us, and x dot at time 0 is given to us, you want to find x as a function of time, correct? So x vector at time 0 is given, x at time 0 is given, x dot at time 0 is given, and so this is an initial value problem. You want to find x as a function of time, okay? That is your goal here. And then find the For instance, the period of oscillations and so on. So how do we do that? First thing is, what is M matrix, what is K matrix in this case? And one of the things I have shown you in my other videos is here you're going to draw 3 separate F.B.Ds for M1, M2, M3. And then from the F.B.Ds, you write 3 separate differential equations, and then you rearrange those equations into this matrix format, and then from there you can find M and K. But here I want to show you another way to do it, which is basically like the last step of all of those. And I want to show you how to get M and K without even drawing F.B.Ds and without even writing the ODEs. Just directly by looking at the system, I want to fill for you the matrices M and K based on these individual M's and individual K's. Okay? So can I do that without drawing F.B.Ds? The answer is yes. Now, one thing I want you to pay attention to is that this system is a vertical system. And although mg initially brings the system down to an equilibrium position, all of these x's are measured from that static equilibrium. Therefore, even if you draw the F.B.Ds, the mg forces will be cancelled by the extra deflections of the springs. And you can just neglect the mg. So the only forces on the m's that you will see are just going to be the spring forces. Now, how do I form M and K? Now, this is a simple 3DOF system. The masses are point masses, so the M matrix is extremely simple. It's a diagonal matrix. And on the major diagonals, you have M1, then M2 and M3, and anywhere else is all zeros. So M matrix is simply a diagonal matrix, right? So in this case, M3 and M1 are 2, and M2 is 1. So that's it. That's your matrix. M, extremely simple. Now K is the one that is a little bit more interesting. Let's look at K. So in the case of K, this is what I want you to pay attention to. K is also going to be a 3 by 3 matrix, but on the diagonals, for each one of these degrees of freedom, the diagonal is going to be sum of all the spring constants that are attached to that mass. Remember that this first column is like x1, the second column is x2, the third column is x3. Also, the first row is x1, the second row is x2, and the third row is x3. So this element 1, 1 is everything that is applied to motion x1. And this is x1 for M1. So here we are looking at any spring that is attached to M1. What are they? It's this guy that is attached, it's this one that is attached, and it's this one that is attached. So in this case, if I want to write it in terms of those K's, what is this first diagonal going to be? It is going to be K1, 0, and then plus K1, 3, and then plus K1, 2. These 3 are attached to it. Each one of them will help bring this guy back to equilibrium, so their K's should be all added together. Okay? And they are all, with respect to M, they are like parallel, so you have to add their K's together. What about M2? Well, for M2, again, look at which one of these springs are attached to M2. So you see that this one is attached, and this one. So element 2, 2 is going to be all the K's attached to M2. So this is going to be K1, 2 plus K2, 3 plus K2, 0. Like this. And finally, for mass number 3, again, all of the springs attached to it. So that's these 3 guys. Again, add them and put them at element 3, 3. There we go. So here are my diagonal elements. Good. Now we are going to look at the off-diagonal elements. The off-diagonals are going to be negative. And for instance, if you look at this one here, this is something between motion x2 and motion x1. So between masses m1 and m2. What is between mass m1 and mass m2? If you look at it, you'll see that that's this spring here. This spring is between m1 and m2. That's k12. And it is basically, since it belongs to the other motion, it is going to be negative. So here, this is going to be negative k12. Use a different color here for you. And then, as I'll show you later, this K matrix is a symmetric matrix. So the spring that you have between 1 and 2 is the same spring that you have between 2 and 1. So between column 1 and row 2, which is this point, this guy here, that should also be negative K12. So there we go. This is also negative and then K12. Similarly here, this is between motion x3 and x1. So between 1 and 3, what do you have? If you look between 1 and 3, you have this guy. So that is k13, but again with a negative sign. So k13 and then k13, but again with the negative sign here. And finally, between here, this is between 2 and 3. And between 2 and 3, if you look, the spring is this guy here. That's between 2 and 3, so K23 and again negative. There we go. This is my K matrix. So the diagonals are some of the K's that are attached to any mass. The off diagonals are with the negative sign, the K's that are between those two motions. Okay, now if there are two springs between those two, like there is another one here, for instance, and this is called K, for instance, something else. K, just K, then you have to add that K here to this 1, 3 and also to this 1, 3 with the negative sign. And you have to add that K also here to element 1, 1 and here to element 3, 3 because that is also attached to 1 and 3. So that's going to show up in 4 different places. Okay, so this is how to get your M and K matrices just by looking at the system. That's all you need to do. Now in this system here, if you look at the values that I provided for these different K's, you can see that my K matrix, this is going to be like 200. Let me clean these up. This is going to be negative 50, negative 50, negative 80, 230, 210, negative 50, negative 50, negative 80. Okay, so I got my M and K. And one thing that I mentioned, and let me tell you right now, is in any free vibration multi-DOF system, which has a governing equation like this, where this X is a vector actually, and the X double dot is a vector, the M matrix is always a symmetric matrix and positive definite. Most of the time it is a diagonal like this. Now you might say, could M be non-diagonal? Yes, it could. I'll show you. So M is not always diagonal. Okay, sometimes N could be a little bit off diagonal. It can have off-diagonal elements, but it's always going to be symmetric and it's always going to be positive definite. What does positive definite means? Means x, any x times x transpose, any vector x times m times x transpose, this quadratic form, is always going to be positive as long as that x is not equal to 0 vector. So if you plug in any non-zero vector in this quadratic form, the answer is always positive. M is called positive definite. What about K? K is also always symmetric and in general positive semi-definite. Under some specific condition, it could be strictly positive definite. So for K in general, x transpose times K times x is bigger than or equal 0 for a non-zero x. Okay, that is the condition. And under what condition this equality goes away and it becomes positive like M? This is if all DOFs are constrained by stiffness. So all of the DOFs should be constrained by some stiffness. And if you look at here, that's the case. If you look at all DOFs, they are attached to the ground and there is even springs between them. So if you look at this matrix here, this K, that K is absolutely positive definite. Okay? Now you might say, well, how do I know, right? This is my M matrix, that is my K matrix. How do I know whether these matrices are positive definite or not? Well, one way is to plug in any arbitrary x, which is in this case 3 by 1. Right, so it's going to be 1 by 3, 3 by 1, form the quadratic term and show that it's always positive. Another way you look at their eigenvalues. Another way is you can look at their determinant of their minors. So if they are positive definite, all of their minors, determinants of them should be positive. In this case, it's obvious. But for the K matrix, what you can do is you can look at the determinant of K itself. You can look at the 1, 1, the determinant of 1, 1, and then you can look at the determinant of this minor 1, 2, 1, 2, right? So and then the whole K itself. If these three numbers are positive, then K is a positive definite matrix. So let me show you that in MATLAB. So this is my K, and determinant of K is, you see, it's positive. The element 1, 1 is positive, and also I want to show you the determinant of K, row 1 and 2 and column 1 and 2. And you see this one is also positive. Also, if you get the eigenvalues of K, you see that all eigenvalues of K are also positive. So this is a positive definite K in this case. Okay, but there could be scenarios where K, not all of your DOFs have a stiffness attached to them. That is very rare that you see that, but if that's the case, then your K matrix could be what? Could be positive semi-definite. And you might say, where? Show me an example, huh? Show me a system where this K matrix could be positive semi-definite. And the answer is, if I show you this system, so this is M1, and then this is the spring, or let me do it horizontally. And this is M2, and this is K. And that's it. No object is attached to the ground. You know, in this system, if you find the K matrix, it is simply going to be a K and a K here, and then negative K and negative K. Because nothing is attached to the ground, and the system can have a rigid motion. It's a degenerate system. And that K matrix, as you know it, this guy is positive, but the determinant of K in this case is 0. So this is and one of the eigenvalues is also 0, which indicates of the system that can freely move in one direction. We call it a degenerate system. So in degenerate system, your K could be positive semi-definite, okay? That is possible. But M is always positive definite. So, and the reason that they are symmetric, I mentioned why, but another way to look at it is the kinetic energy of your system, T, is 1/2 x dot vector, and then M times x dot, and this is a transpose. So that's the kinetic energy of the system, and kinetic energy, always has quadratic terms in it. Therefore, the M matrix has to be positive. And then the potential energy of the system due to springs only is 1/2 x transpose times K times x. And again, the spring potential energy is also quadratic in terms of x, so K should also be symmetric as well. Okay, so because of the relation between mass matrix and kinetic energy, and stiffness matrix and potential energy, and the fact that they always have quadratic terms, we can see that Y, M, and K matrix have to be symmetric. So these are about the properties of M and K, and this is the M and K for this specific system. So far, okay? Now let's move on to the next topic. So what would you do next? Next, we have to find the natural frequencies of the system and the mode shapes. Then we are going to look at properties of the mode shape. So this part is done. Now I want to go here and see if the mode shapes have any specific property. Then we are trying to find the response of the system with these initial conditions, and then finally we're going to look at the period of oscillation for this system. So we have a lot of things to cover, okay? So let's go ahead and find the natural frequencies and the mode shapes. How do we do that? Well, what we need to do is to find the M inverse times K matrix, and then from there, from the eigenvalues and eigenvectors of that, we can find the natural frequencies and the mode shapes, correct? So let's go ahead and do that. So here what we need is the M inverse times K matrix. We find it in this system, and then the eigenvalues of that, as you know, they are the natural frequencies of the system squared, and it also had eigenvectors, which are going to be the mode shapes of the system. We can maybe show them with phi I. So let's go ahead and do that, and for that we can use MATLAB. So here, this is my K matrix, if you remember, and this is my M matrix. So I get this A matrix and call it inverse of M times K, or if you don't like it, just say that V and D, or if you don't want to call them V and D, say call them phi and lambda, right? Equals eigen of inverse of M times K, okay? There we go. So these are the eigenvalues, of course written as the matrix, so all you care about are these diagonals. And these diagonals, remember, these are not natural frequencies, these are natural frequency squares. So you have to take a square root of them to find natural frequencies. And then each one of the columns here in this guy is one of your mode shapes. So this first one is for the first frequency, the second column is for the second frequency, the third one is for the third frequency. So first thing I do is I get the diagonal elements of lambda, which are these three numbers, and then I take a square root of them. So first thing is, you see my frequencies, 7.43, 1139 or 40, and 1549. These are the frequencies in radians per second. So I move my MATLAB to a secondary window, and I want to write these numbers for you. So what are my frequencies? This one, the first one is 7.429. The second number is 11. I use 3 decimals here, 398. The last one is 15.489. And frequencies is always increasing from the first one to the last one. Now the first mode shape is the first column vector of that phi matrix, which if I write it for you in this case, that is going to be 0.618. And then 0.509, and then 0.599. Then here we have 0.723, negative 0.207, negative 0.659, and the last one is 0.12, negative 0.952, and 0.281. Okay, so these are omega 1, omega 2, omega 3. And these are the mode shapes, phi 1, phi 2, and phi 3. So we found the natural frequencies and the mode shapes for each natural frequency. Clearly you see that the frequencies are always in an increasing order. Now, is there anything specific about these 3 vectors, these mode shapes? Is there anything specific about them, or anything specific about this matrix that has the mode shapes in it? This matrix phi here, which we call, by the way, the modal matrix, the matrix formed by these phi's, right? So if I put these phi's together, my phi matrix, which is going to be vector phi 1 and phi 2 and phi 3, this is what we call the modal matrix, which is the matrix of mode shapes. So is there anything specific about this matrix or these vectors? The answer is yes. What is that? First is, if you look at the magnitude of each one of these columns, the magnitude of each column is 1. And that should be because MATLAB, when it returns any of the mode shapes, it always gives us the mode shape that has a magnitude 1. So we say it normalizes the mode shapes, right? So look here, if I say what is the norm of phi column 1, you see it's 1. If I do it for column 2, it's 1. If I do it for column 3, it's 1. So the ones that MATLAB bring to us, these mode shapes, are what we call normalized mode shapes, because their magnitudes are also all 1. Now, what about their product? If I do a dot product between any 2 of them, would you get 0? In other words, are these mode shapes perpendicular to each other? The answer is not necessarily. So here I look at the dot of column 1 and column 3. Yes? And you see the answer is not 0. I can do it between column 2 and 3. It's not 0. It's small but not 0. And then if I do it between 1 and 2, also it's not 0. Could be small but not necessarily. So the mode shapes are not perpendicular to each other, but I want to show you something interesting. What if I multiply, for instance, mode shape 1 vector multiplied by the M matrix, then multiplied by mode shape 2. And for that, I need to transpose this. So I transpose mode shape 1 multiplied by M multiplied by mode shape 2. Look, 0. What if I do it with mode shape 3? 0. What if I do it with mode shape 2 and 3 instead of 1 and 3? 0. So you see, although each mode shape is not perpendicular to the other one, but if I put M in between and then do the dot product, so basically form these guys, phi transpose M another phi, where I and J here are two separate mode shapes, so phi I transpose M phi J, the answer is always 0. So we say the eigenvectors or the mode shapes are orthogonal with respect to M. They are orthogonal with respect to M, and that is something that if you studied linear algebra, that's the terminology in linear algebra. If phi I transpose M phi J is 0, then we say phi I and phi J are orthogonal with respect to M. Okay? And not only that, also with respect to K, these mode shapes are orthogonal too. They have K orthogonality. So if instead of M, I use the K matrix here in any of these, the answer would also be 0. Look, here, that's K, and then that was between 1 and 2. Let's do it between 2, 1, and 3, and let's do it between 2 and 3. Now you might say, why is it not perfectly 0? The reason is numerical error, okay? Because when we calculate these numbers, they are only calculated up to 2, 3 decimals, and then there is round-off error. So when you see these very small numbers, they are practically 0 if you could calculate them up to infinite decimals, which you cannot. So it's just round-off errors is what you can see here, but they're all 0. So the second set of properties that you learn here is, with respect to the K and M, the separate mode shapes are, of course, what? They are, of course, orthogonal. Now, you might say, what if I use the same mode shape? So here, I use this, but I use phi 1 on both sides. What's going to happen? So if I use phi 1, transpose M phi 1, then I get 1.74. It's not going to be 0, and if I do it for phi 2, it's not also going to be 0, and if I do it for phi 3, it's not going to be 0. So it's only for different phi's, not the same phi's, okay? So I and J, as I mentioned clearly here, I and J should be eigenvectors corresponding to separate eigenvalues, to distinct eigenvalues, okay? Yes? So that is another property of these, and you might say, so what? They have this property, where would you use it? I'll show you. Use that in modal analysis. I'll show you in a second. So this is a very important property. This guy here and these guys, these are important properties that we are going to use in modal analysis. So far, I found for you the natural frequencies and the mode shapes. And I showed you that mode shapes of different frequencies, they are perpendicular with or orthogonal with respect to M and K. Okay? So now that we have seen this, let's go to the next step. What's the next step? The next step is, now give me the solution. What is the solution? So here I want x1 of t, I want x2 of t, and I want x3 of t in the system. Tell me what are these solutions versus time if these initial conditions are given in the system. How would you do that? And the way we want to do it is with modal analysis. You know, in general, you can do it without modal analysis. How? So what you can do is, you know, the solution to x vector, if you put all of them in vector x, the solution to vector x is going to be basically a constant like a, which you don't know, times mode shape 1, and then this is times sine of omega 1t plus some angle, you might call it theta 1 for instance, and then plus another constant you don't know, b, times mode shape 2 times sine of omega 2t plus angle theta 2 and then another constant c you don't know times mode shape 3, and times sine of omega t times t plus omega 3 times t plus theta 3. Okay, and these guys you also don't know, these thetas, these phases. Or you can write it as a combination of sine and cosine and get rid of that theta. So here you have 6 unknowns, a, b, c, and theta 1, theta 2, theta 3, 6 scalars that you don't know and you can find. And these 6 scalars are coming from these 6 initial conditions that I highlighted for you, these guys. Okay? So they can come from these 6 initial conditions that you have in the system. That's one way to do it. Another way is, since this one involves a lot of parameters that are not easy to find, especially the thetas, which you will involve sine and cosine of theta in it. So it's not really easy to find this. A better, more efficient way of solving for these is the modal analysis. So how do you do that? Well, if you look at your original ODEs are coupled, right? They are coupled. How do you know they are coupled? Because you have off-diagonal members. Remember? You have off-diagonal members because these guys are not zero. So your ODEs are going to be coupled to each other, right? In the equation of x1, there is x2 and 3. In the x2, there is x1 and 3. In x3, there is x1 and x2. So it's not really easy to solve these equations, correct? It's absolutely not easy. For instance, if I just show you the first ODE is like this. 2x1 double dot, and then plus 200 times x1 minus 50 times x2 minus 50 times x3 equals 0. You see, second order ODE is linear, but these two guys appear in that first ODE. Or the second one, if you look at the second row, it is 1 times x2 double dot. You might say, where do you get this 2 and 1 from? They are coming from the M matrix. So that one, and then minus 50 x1, and then plus 210 x2, and minus 80 x3, that is equal to 0. You see that? That's my second one. And if you want, let me also add third one. Now that I wrote everything, let me also write this. So the last one is like this. So you see, I have 3 coupled ODEs. I cannot solve any of them individually. And even if I plug this general solution in it, and then finding all the ABCs and the thetas. So another way is I'm going to convert these ODEs into the equations in which these are going to be 3 new ODEs, and in those ODEs, if you call the new variables instead of x1, 2, 3, call them q1, q2, q3, the first one is going to just be something like some number times q1 double dot plus some number times q1 equals 0, and the second one is something similar. And the third one is, again, going to be something similar. So what, and these numbers are different, okay? Each one has a different set of numbers. So I'm going to convert these 3 coupled ODEs into decoupled ODEs. Now each one of these ODEs can be solved separately, And once you have them, you can come back to these. So these Q's and the X's are related. I'll show you how to relate them and how to solve the solution here, because the solution is much easier here. This is very easy to solve. These are like three 1-DOF systems. So you can solve them individually, right? This is like 3 1-DOFs. That is like 1 3-DOF. You solve it and then you go back. How do you do that? This is what the basis of modal analysis. So let me show you how to do modal analysis here. So this is the way you do it. You come and here we have some definitions. So phi here is the modal matrix, the matrix that you put together by putting all the eigenvectors or the mode shapes in a matrix. That's the modal matrix, right? That's phi. I introduced it to you. Lambda is going to be the matrix of the omega squared, right? So basically phi and lambda are the same thing that I showed you in MATLAB. Remember? When we ran this command, look, lambda is the diagonal with eigenvalue squared in it, and phi is those 3 mode shapes or 3 eigenvectors, right? So this is the phi and lambda that I'm talking about. X is the solution to be found, and vector x0 equals all of the solutions at time 0. Vector x dot 0 is all of the x dot at time 0. These are given to us. So these guys are given. We know them. The phi's and the omegas we already found from the M and K matrix. The goal is to find x of t. That is the problem we are solving. Now, how do we solve it? Here, instead of solving it directly for x, I'm going to transform my variable from x to the new variable q, where x is equal to phi times q. And what was phi? Phi was the modal matrix. So I say, if x is phi times q, what's going to happen? By the way, this q that you get from here, it's called the modal coordinates. So instead of x, which was the standard coordinate that we used, this q vector that you get from here, this q is what we call modal coordinates. These are the coordinates in which the ODEs are separated, are basically decoupled. So these coordinates are what we call modal coordinates. Now, I claim that the way to get these modal coordinates is through this transformation. How does it work? I'll show you why this transformation does work. So I say that, well, go ahead and plug that x into the equation. So wherever I have k times x, for that x, I'm going to plug it in. Also, I need to take 2 time derivatives from this. Why? Because I need x double dot. So from here, you can see that x double dot is going to be, because phi is a bunch of constant numbers, is going to be phi times q double dot. So that one is going to sit right here. And they are multiplied by m and k, so we get m phi q double dot plus k phi q equals 0. So now this is my equation in this new system. Then what? Then I pre-multiply both sides by a phi transpose. So it becomes phi transpose m phi q double dot plus phi transpose k phi q equals 0. So this is my equation now. Now, if the mode shapes are mass-normalized, which means phi transpose m phi equals I and phi transpose k phi equals lambda, then that equation becomes like this. You might say, where did you get that one from? What does mass-normalized mean? What is this? Well, here is the place that you need to go back and look at these 2 important properties that we found. That individual phi's, if you transpose them and multiply them by m and multiply by another phi, the result is 0 for different I and j. If I and j are equal, then the result is not necessarily 0 as I showed you. So when I do the whole matrix phi transpose times m times phi, what that is going to do, it is going to be something like this. In the 1,1 element of that, it is going to be like phi 1 transpose, where this is the vector, times m times phi 1. Okay, that's element 1,1 of that. What's element 1,2 of that? That is going to be phi 1 transpose m phi 2, phi 1 transpose m phi 3. And similarly, right, this is phi 2 transpose m phi 1, phi 2 transpose m phi 2, phi 2 transpose m phi 3. And let me also add that last one. Sorry for my bad handwriting. There we go. So what would you get? Well, guess what? All of these off diagonals based on this property that we just looked, they're all going to be 0. So what you will get is 0, 0, 0, 0, 0, 0. The diagonal ones are not going to be 0. Yes? Similarly, if you do it for k, so if you grab this whole thing and do it for the k matrix, so anywhere you had m, now you can replace them with k, the result is going to be similar. So let me plug in k. Again, all the off diagonals will be 0. Now, what about the diagonals? The diagonals don't need to be 0. But what would they be? They are not 0, but what are they equal to? Yeah, remember that your M inverse K matrix, the eigenvalues of that were these omega squareds. So this was like omega 1 squared, and then omega 2 squared, and omega 3 squared. All 0, that was the lambda matrix. So you might say, well, what about here? What can you do here? Okay. Well, in this case, if I change my M matrix such that the diagonals become all 1, then all of the K's can become lambda. And you might say, well, how does that happen? Well, this is happening when it is mass normalized. And you might say, how do I mass normalize it? It's not very hard. How do you do that? All you need is to get these numbers that are non-zero. Okay? So each one of them is a scalar number. If you take a square root of each one of them and divide these original mode shapes by those. So here, divide this by square root of phi 1 transpose times m times phi 1. this one divided by phi 2 transpose m phi 2, and this one by square root of phi 3 transpose m phi 3. And the reason you do square root is because in here you have a quadratic form, so that square root and that square root multiplied together becomes just 1 over that, and here that m has that those diagonal elements, so when these two phi's are multiplied you get 1 over that element, so 1, and then that number is divided by itself, you get a 1 as identity matrix. So going through this, as I said, this thing here is called mass normalization. So let me show you what that means. So this is my phi matrix. The other thing I need is I need to multiply phi transpose by m by phi. Remember, as I said, all the off diagonals are going to be 0. These diagonals are going to be non-zero. These are those numbers, you need the square root of them. And once you have those square roots, then this first column have to be divided by square root of that. That second column has to be divided by this square root. And the third column has to be divided by this square root. Okay? And if you put those new phi's in a matrix, that is the mass-normalized matrix with mode shape. So let me do that. So I say I create a new phi matrix, and this is equal to basically divide phi column 1 divided by square root of what? This answer, this matrix, whatever it is, element 1 and 1, which is that. So I divided by that the square root. Then I repeat that for column 2. I divided by square root of this guy, which is element 2, 2. And finally, I divide column 3 by the square root of element 3, 3. And this guy is going to be my mass-normalized mode shapes. So these three, if you look at them with the original one, these are mass-normalized. Now you might say, if I calculate this right now, would that give me identity matrix? Well, let's take a look. Boom, it does. And you might say, if I put k in here, what would it do? If I put the k here, what would it give me? It gives me this. Now remember the lambda matrix. Look at that. That's the same thing. You see? So if I mass normalize my mode shapes, then phi n transpose k phi n, where phi n is this mass transform version, mass normalized version of the phi's. That is going to be the lambda matrix, and for m, it's just going to be the identity matrix. So the first thing I do here is, in this equation, I make sure that each phi is mass normalized. So each phi is whatever the original phi was divided by that square root. And what was that the square root? That the square root was basically phi I transpose times m times phi I. So this is called mass normalization, okay? I do that. If I do that, then I get these two beautiful conditions. And now the good thing is this. This is now a diagonal matrix. This coefficient is going to be a diagonal matrix, and it's going to be identity matrix. So if I expand this, in the first row, I only have Q1 double dot, second equation only Q2 double dot, third equation only Q3 double dot, like this. And what about this guy? This guy is going to be lambda matrix, and lambda matrix is also a diagonal matrix, right? So it is like lambda 1, lambda 2, lambda 3, everywhere else 0. So if I do that, then This is going to be in the first row only lambda 1 Q1, in second row lambda 2 Q2, and then lambda 3 Q3 in the third row. So if I expand these equations, each equation is going to be a separate, basically decoupled ODE. You see here in each QI there is only that QI, no other QI. And these omega i's are those squared are the lambda i's. So you see, now I could turn my ODEs into n decoupled ODEs. And if I have the initial condition for these guys, based on what you learned in my video on single DOF systems, you know the solution, right? You know what's the solution to this. What's the solution to a single DOF ODE like that? Well, if this is subjected to Q0 and Q dot 0, right? So this is Q at time 0. This is Q dot at time 0, or QI dot at time 0. If they are like that, the solution is this. QI0 cosine omega it plus QI dot 0 over omega I times sine omega it. Right? This sine term is due to initial velocity. The cosine term is due to initial displacement. The only thing is, how do I get these two? And the answer is very easy. All you need is to find them from their transformation equation. What was your transformation equation? Well, that was this guy. X was phi times Q. So from here, what is Q? So from here, you see that Q is, to get that, the best way to do it is I multiply both sides by M, then I multiply both sides by phi transpose. Why do I do that? Because if you remember, this guy is now with this mass-normalized thing, this is going to be identity matrix. So on the right side, I get Q, and on the left side, I get phi transpose M times X. So Q equals phi transpose M times X. And if I want the initial condition, I just plug in initial condition. So Q at 0 equals phi M X at time 0. That's all I need to do. And that is exactly what you can see here. Look at that. And if you take a time derivative from that, since M and phi are constant numbers, then Q dot at time 0 is phi transpose M X dot at time 0. There we go. So since these guys are given to us, and we have the phi and the M, by the way, this phi is that phi n that I have in MATLAB, the new one, the mass-normalized one. So here we go. I got my new initial condition in this system, and now I'm going to plug them in. And I get my solution to the modal coordinate. So now I have my full time solution to the modal coordinate. But the initial goal was to find X, but X was simply phi times Q, so I multiply both sides of it by a phi. And since each one of them is one solution, then X is the total of them. So I can say that the total X is summation I goes from 1 to n of each one of the phi's times the corresponding Q. And that is my total solution, X of t. Boom, done. Just pay attention that these phi's are all mass normalized that you're using here. So I solved my ODEs individually using modal analysis. I converted my ODEs into individual decoupled ODEs. I solved them. Once I solve them, I put them back into the original transformation, and now I get my solution in the original system. So it's a perfectly systematic thing. You can have your computer do that, and it's very, very easy to do it rather than going back to this original form that I showed you here. Where is it? This one. And in these guys, considering that solution that involved this one here, and then solve for A, B, C, and all of the angles. That's much, much easier than this. especially as your degrees of freedom gets bigger and bigger. This becomes almost close to impossible, while this one can always give you a solution, and this one always have a solution. And here in this bottom row, basically the qi0 and qi.0 are replaced by these. So this is your final form of solution, which is always doable. And this technique is called the modal analysis here. Okay, so let's go ahead and apply that to this problem with those initial conditions and the m and k and these new phi's. We are going to basically find my responses of this system to those initial conditions. So let's go ahead in MATLAB and do that. So this is my vector of x zeros. This is my vector of x dot zeros, right? These are these set of initial conditions here. And now what we need to calculate are these terms. We need to calculate this and this. So first, let's do this. These new phi's, we transpose them. We multiply them by m and then by x0. And that should give me 3 values, right? So one for phi 1, then for phi 2, then for phi 3, and then we multiply them by phi. So if we expand this, basically, this is going to be like phi 1, right, times something. By the way, in this system, since all x dots are 0, this whole term will be 0. Okay, that makes life a lot easier for me. So that is going to be phi 1, and then here is going to be phi 1 transpose times m times vector x0, and this is times cosine of omega 1t, and I don't even need this. And then if I expand it, it's going to be phi 2 transpose m again x0 times cosine of omega 2t, and finally phi 3. There we go. So that is all you need to calculate. These are the terms that you need to calculate and add them together. That is going to be your solution. So let's go ahead and do that. So those phi's are the columns of this new phi n. So like for instance, phi 1 is the first column of this matrix. That's phi 1. The second column of that is phi 2. And the third column of that is phi 3. So now all I need is to calculate phi 1 transpose. So here we go. Phi 1 times phi 1 transpose times m times x0, which we have. And that is this guy. This guy is going to be multiplied by cosine of omega 1t, and that is the solution for all 3 x's. So if I want to expand that, I can say, in this case, my x1 of t, my x2 of t, and my x3 of t are going to be those numbers that you just saw, each one of them times cosine of omega 1, omega 2, and omega 3 times t, and we have these omegas here. Now in this case it's just omega 1, so 7,429 times t, and the exact same thing for these guys. And those coefficients are these numbers, right? So let's write them down. So here I rounded them to 3 decimals, and these are this first term, that's this one here. then I need to repeat that, but this time for phi 2. So I repeat the same thing, and I'll do phi 2. And these coefficients are for omega cosine omega 2t. So here I'm going to add them. So it is going to be positive 0.068 cosine of omega 2t. And then this is negative and this is negative. That is this one. And then finally, we are going to do phi 3 here. So let's do phi 3. And these are these coefficients. So let's go ahead and write them. So plus 0.097 minus 0.768 and minus or plus 0.227. And these are going to be cosine of omega 3t. There we go. So these are your solutions, x1 of t, x2 of t, and x3 of t in response to these initial conditions based on the modal analysis. Okay? Yeah, so you see, finding these solutions based on modal analysis is completely doable and you can do it. And we do not need to do any extra phase here and then can use trigonometry to convert sine into cosine. All we do is directly solve the equations in this decoupled space and then bring them back into the original one, and there we go. So this can be easily programmed, and you can solve them analytically like this, as long as you can mass normalize this phase, okay? And that is what we did here. Okay, so we did this part as well. Now, what's the only part left? The only part is the period of these signals. So let's go ahead and plot one of these and see if we can find the period of these signals. Because you have three separate frequencies. You have this frequency, you have this frequency, and you have this frequency. So here you have three frequencies in your responses, and you want to plot one of these, see how it looks like, and then if you can find the period for that function. Is that function is going to be periodic? And if it is, what's the period of that function? So for that reason, here I'm going to plot it in MATLAB, and let's say here I give it a time range from 0 to, I don't know, maybe 100 seconds with an increment of 0.01. So my x1, and here I'm typing on the side. Let me bring my MATLAB here. Maybe this can help a little bit better. Let's move this to this side. And let's put this MATLAB on this side. So you can see, so it is like this times cosine of 7.429 times t. And then I'm gonna repeat the rest of it. So and then the last one, which is 0.097 times cosine of, and that one was 15,489. So that's x1, and now let's go ahead and plot t and x1, maybe with a line width 2. So that is the signal. That's how the signal looks like. And you might say, does the signal look like it is repeating itself? So maybe we can look at a shorter range of time, maybe 10, 20 seconds, 30 seconds, something like that. See if the signal seems to be repeating itself. So this is your signal. Okay, this is the response of the system, and can you see that the signal is exactly repeating itself at any point? Can you find any 2 points that are exactly like each other, and any time point after that is the same signal? And it's not really easy to find such a thing, because if you look at these amplitudes, they keep changing. They do not stay the same level. And again, if you look at a bigger range, right? So you might say, what about this? Do you see anything? Okay. So for that, I need to tell you a little bit theory about this, and then we come back and revisit this problem. So if in general, and here we're just going to look at 2 harmonics instead of 3, we look at a simpler case. So if any response in any system has 2 harmonics, like A sine omega 1t plus B sine omega 2t, or they could be cosine, it doesn't matter. And omega 1 and omega 2 are the 2 frequencies in the response. So if somebody says, what is the period of a signal like that, what's your answer? Well, that depends on whether these 2 frequencies are what we call commensurate or incommensurate. What does commensurate means? Means the ratio is a rational number, it's the ratio of 2 integers, or incommensurate, like it's not. If the ratio is commensurate, so omega 1 over omega 2 is like m over n, where m and n are integers. Okay? Yes? Then the signal is periodic, and the fundamental frequency of that, the smallest frequency of that, will be 2 pi times least common multiplier of 1 over omega 1 and 1 over omega 2. For instance, let's say omega 1 is what, 6.5, and omega 2 is like 2. You might say, well, clearly, if one of them was an integer multiple of the other, then you can definitely use the smaller one in this case. Okay? And put it in the denominator. But, so if one was like 6, one was 2, then one of your periods is 2 pi over 6, the other one is 2 pi over 2, so clearly the smaller one, the bigger one, is going to be your fundamental frequency, if one was an integer of the other one. But in this case, it's not. So one of them is not a basically factor of the other one, like this. The ratio between them is not a single integer, but it can be written as the division of 2 integers. Like what? Well, look at this. If I multiply both by a 2, this is going to be like 13 over 4. So you see, omega 1 over omega 2 can be written as the ratio of 2 integers. Therefore, the ratio of these two are commensurate. Okay, these frequencies are commensurate. So what would you do in this case? Then we do a least common multiplier of 1 over 2 and 1 over 6.5. Okay? So we need to find the least common multiplier of those, and we multiply that by 2 over pi, and that should be basically the answer. So now comes a bigger question. We are just constantly opening the basically can of worms, huh? So how would you find this? What is the LCM of 2 ratios? So LCM of A over B and C over D can be written as LCM of A and C over greatest common denominator of basically B and D. Okay, so in this case, you have 1 over 2 and 1 over 6.5. A and C are 1 and 1, so your LCM is simply going to be 1. And then what is the greatest common denominator of B and D, which in this case are 2 and 6.5. Okay, so what is, if this is a 2 and this is a 6.5, this is 1 and 1. Which number can you divide both 2 and 6.5 to? Okay, it could be a factor of them, and in this case it doesn't have to be an integer, and the answer is 0.5, is something that these two can both be divided by. So the answer in this case is 2. So your answer is 2 pi times 2, it is going to be 4 pi. Okay, so for that signal, if the signal is like this, A times sine of basically 2t plus B times sine of 6.5t, if that is your signal, then the fundamental frequency is going to be 4 pi. Okay, this is for the case that they are commensurate. The ratio is the ratio of two integers. Now, if they are not commensurate, guess what? If it's not a rational number, then the signal is not even periodic. And there is no period, of course, because the signal is not periodic. Okay, it's not periodic. So what do we have in this case? Look at my numbers. 7.429, 11.398, and 15.489. Here you need three ratios really, right? Because we have three sets of frequencies. So you need omega 2 over 1, 3 over 1, 3 over 2, and all of them should be commensurate. And in this case, they are not, okay? You cannot find two integers that fits all of these three ratios, and for that reason, this signal is aperiodic. You might say that looks kind of periodic. Yes, it is, but you cannot, again, see a pattern completely repeating. Look at that. You might say, well, look at that. That does look like, no. Look here, it goes up, stays flat, goes down. Here it goes up, then flat, then down. But look at the amplitudes. Look at these two amplitudes and these two. They are not the same. You can always use your data cursor, right? So look at this third value here, and then use your Alt and set another one here, right? And you're going to see that the numbers are not the same. Look. So this one is 0.169, this one is 178. They are not the same magnitude. Okay, and even if you keep any further, you're not going to see necessarily anywhere that the two signals are exactly repeating themselves. Okay, so this is something that you need to, if somebody asks you what's the period of this, is this a periodic motion? Well, kind of looks like one, but not exactly. It's not perfectly periodic. Okay, it's basically what we call semi-periodic motion. So hopefully you learned all of this material in one video. I know I did a lot here in this video. I showed you how to get M and K without even writing the ODs and getting the free body diagrams, how to get a solution for this system by modal analysis, what were the properties of M and K, what were the properties of mode shapes, what is mass normalization, and what is the period of the signal if there is any. So hopefully all of this material was useful to you, and I'm going to see you in the next video. Thank you.